Hello, this is Roger Scheffler again, and in this session we will review the first 5 principles of the AMI equipment design checklist. Principles 6 to 10 will be then covered afterwards by Kari Rasmussen in the following session right after this. The learning objective for you will be to get familiar with the equipment design principles 1 to 5 in combination with reviewing practical examples for each principle. In the introduction, we talked about various hygienic design principle resources like AMI, GMA/CBA, or AHEDGE. Here and now, we will dive deeper into the AMI equipment design checklist. In this checklist, there are 10 main principles included. And under each principle, there are multiple sub-principles that result in almost 80 guiding principles in total. When using this checklist to assess the hygienic design level of food processing equipment, it is recommended to use its rating system as a helpful tool. The rating system works like this. Each principle has got a number or value assigned to it, so-called points available. As an example, like here on the screen, you can see that the principle 1.1 has the value of 20. Now you get into the evaluation. When looking at your equipment, you may rate this as 20 when you think all requirements are fulfilled and no design flaws exists. In that case, you would rate it as S, like satisfactory, with full points of 20. If you think there are a few design flaws, then you may give it an M for marginal, resulting in half points, equal to 10 in this example. However, if you think the design features are not met, then you may rate it as U, like unsatisfactory, with 0 points. If this example, however, doesn't match that piece of equipment, then you rate it as NA, not applicable. At the end, you will have a total score of all 10 main principles, which serves as a good base for setting up a plan to be designing out, for instance, or more improvements. Let's go through each principle one by one. Cleanable to a microbiological level. Made of compatible materials. Accessible for inspection, maintenance, cleaning and sanitation or disinfection. No product or liquid collection. And number 5, hollow areas should be hermetically sealed. Principle number 1. Cleanable to a microbiological level. Food equipment must be constructed to ensure effective and efficient cleaning over the life of the equipment. Equipment should be designed to prevent bacterial ingress, survival, growth and reproduction on both product and non-product contact surfaces of the equipment. When we talk about cleanable to a microbiological level, accessibility for cleaning is very important. Imagine if you cannot access some areas of the equipment for cleaning, or you can't even see it, how can you make sure it gets microbiological clean? So all surfaces of equipment should be accessible for cleaning and disinfection. Good accessibility facilitates cleaning, which can prevent the formation of biofilms. On the left-hand picture, you see a sanitor trying to clean a piece of equipment. It is hard for him to reach the equipment, in this example a motor cover, so you can see him working on his knees with the risk of touching the floor, which may introduce cross-contamination risks. The right-hand picture shows a nicer example, as the equipment is easier to access and to clean, and there is no need to touch the floor. Principle number 2. Made of compatible materials. Construction materials used for equipment must be completely compatible with the product, environment, cleaning and sanitizing / disinfecting chemicals, and the methods of cleaning and sanitation / disinfection. This principle covers materials that are not accepted to come in contact with food. Materials containing antimony, arsenic, cadmium, lead or mercury. Materials classified as hazardous substances such as carcinogens, mutagens and teratogens. Asbestos and asbestos-containing materials. Wood, enamelware, porcelain, leather, glass. Uncoated aluminium, aluminium alloys, anodized aluminium. Copper and alloys, bronze, brass and zinc galvanizing. Another sub-principle of principle number 2 says composites and plastics remain intact without changes in shape, structure and function through cleaning and sanitation disinfection protocols. Plastics are made of acceptable materials per standards and regulations relevant for the region where the equipment will be used. These pictures gives us examples on how an overuse of chemical concentrations and too high temperature affect plastic materials. For the left-hand picture, it is an example of a modular plastic belt showing signs of chemical attack. The right-hand picture illustrates plastic rollers that had been submerged in a hot water bath within a packaging shrink tunnel application, resulting in dents on the surfaces. Principle number 3. Accessible for inspection, maintenance and cleaning / sanitation or disinfection. All parts of the equipment shall be readily accessible for inspection, maintenance, cleaning and sanitation / disinfection without the use of tools. Let's have a look at 2 examples on poor accessibility. On the left-hand picture, we see 2 people that had to crawl under the machine and 1 person is sitting on the floor. First of all, they may contaminate themselves and subsequently other areas. Secondly, to get there, they very likely had to touch the floor, contaminating themselves heavily prior to touching the equipment. They can't reach all the way into the chute, so they can't clean off possible biofilms. And if the task is that difficult, they maybe cannot clean it thoroughly. The right-hand picture shows an example of a drive end of a conveyor with a small cleaning window at the side. It is very obvious that getting to the sprockets is going to be very difficult. In order to get access to the sprockets, you would have to disassemble those, which would require extra tools to use, which is also not recommended. Product zone components with inaccessible surfaces, for instance, do not allow penetration of detergent. Equipment disassembly is tool-free and as easy as possible. On the left-hand picture, you can see a threaded tension device at a flat belt going into a hollow sleeve. There is a significant risk that product residues, other soil or moisture, can ingress into the hollow sleeve. On the right-hand picture, we can see a nice example of tool-free disassembly. There is a conveyor with an idle roller, a scraper and a return roller, all easy to remove for a thorough cleaning. No tools are required to remove those as they are easily hooked in by design. Product zone components with inaccessible surfaces, for instance, do not allow penetration of detergent. Equipment disassembly is tool-free and as easy as possible. On the left-hand picture, you can see a threaded tension device at a flat belt going into a hollow sleeve. There is a significant risk that product residues, other soil or moisture, can ingress into the hollow sleeve. On the right-hand picture, we can see a nice example of tool-free disassembly. There is a conveyor with an idle roller, a scraper and a return roller, all easy to remove for thorough cleaning. No tools are required to remove those, as they are easily hooked in by design. All surfaces should be designed to eliminate water pooling and be self-draining. Left image is a good example. The cover of the control box has a sloped design to prevent water collection and pooling. Right images are design examples of pieces of a CIP system. If we use the concentric reducer design for horizontal pipes, the draining should be a problem, which causes the product's collection. Better to design an eccentric reducer where water pooling is eliminated. This sub-principle talks about framework. Framework used for horizontal members is rounded. If square or rectangular basis is used, the surfaces are angled so water will drain and not pool. We recommend that equipment framework is constructed from solid stainless steel. Recognize that this may not always be possible on all items for reasons of strength and support. The image illustrates the use of round frame members in conjunction with solid structural frame members with angles to help reduce the risk of product and pooling water. If square profiles are used, turning to a 45-degree angle to prevent surface accumulation is advised. Principle number 5. Hollow areas should be hermetically sealed. Hollow areas of equipment such as frames and rollers must be eliminated wherever possible or permanently sealed. Bolts, studs, mounting plates, brackets, junction boxes, nameplates, end caps, sleeves or other items must be continuously welded to the surfaces, not attached via drilled or taped holes. All rotating members such as drum drives, sprockets or support rollers are solid or fully sealed. On the left-hand picture you can see a crack on a hollow roller, which could be a niche and harborage area for soil collection and microgrowth. A solid roller, like shown on the top right picture, is a better choice from an hygienic design point of view. To use an electrical drum drive in IP69K is another good example for hygienic design on waterproofing. IP69K is the recommendation for wet-washed areas with pressurized water. All stationary hollow tube construction, such as frame members, are fully sealed with continuous welds to prevent interior contamination. Hollow areas are not acceptable at or above the contact zone. Hollow support structures represent contamination risk in food production areas. If used, make sure it is fully sealed with continuous welds to prevent interior contamination. In wet environments, hollow structures may contain water and soils, introducing microbial issues. Potential pest issues can occur in a strictly dry environment. The photos display a situation that can be associated with unsealed hollow profiles. That brings us to the end of this module. In conclusion, in this module we have reviewed the first 5 principles and practical examples related to the principles. I hope you enjoyed the session and may make use of the learnings in the near future. As announced earlier, next session is on design principles 6 to 10. Thank you very much for watching.